Hello YouTube. In this video we're going to be discussing some very elementary properties of radicals and just kind of introducing the concept of a radical. Okay, so we're going to go ahead and get started by defining it as this. A number r, we say the number r is a square root of a number s if r squared equals s. Okay, that is, I write it a little bit differently there. I could say r squared equals s, then r would be the square root of s. Okay, so let's introduce ourselves to some notation here. Okay, so starting with the fact that maybe the radical sign, okay, this is referred to as a radical sign. So this is our radical, okay, and we could also pronounce it as like the square root of something. But let's say we take the square root of 9. Now recall that we said that we say r is the square root of this number s if we can square r and get the number s here. So 9 is like our s in this instance is what we're saying here. So we say, so what is the square root of 9? The square root of 9. What we're really looking for here is the number that when we take it times itself we get 9. So I want to recognize a few things here. If we took 3 squared we would get 9, but also that if we took negative 3 and we squared it we would also get 9. Okay, so we say the square root of 9 is positive 3, but it's also negative 3, and the reason behind this is because we could square a negative 3 and get 9 and square a positive 3 and get 9, so we'd refer to this as the root of 9. Okay, so what other things do I want to mention about this radical symbol here? Well, we say this is some radical expression, but the stuff on the inside of the radical here, we refer to this as the radicand, okay? Kind of like when you divide, you have a dividend. This is like the radicand, okay? And yeah, we say, okay, so every positive number that is in the radicand has 2 square roots. So we'd say in general. So let's write this out. In general, we would say that so long as s is a positive number, then the square root of s has 2 roots, and that would be positive r and negative r. Or we could say, you know, the square root of s has a positive square root of s, and it has a negative square root of s. But every positive number inside of a radicand has 2 roots. Okay, so we're going to go ahead and kind of explore some properties of these, starting with just evaluating some simple ones, starting with maybe up here we say radical 36. So square root of 36, we're really asking the question, what number could we take times itself to get 36? And we say, well, you know, this could be a positive 6 or a negative 6, simply put. But I introduced this example because I want to, you know, discuss maybe a property of radicals, and that is this. We say, well, square root of 36, that's the same thing as the square root of 4 times 9, because 4 times 9 is 36, and I'm picking on 4 and 9 on purpose here because of this. Really, you might recognize that square root of 36 is 6, but this property of radicals says that the square root of a product of 2 numbers is the product of the square roots of the numbers. So you'll recognize here the square root of 4. Well, the square root of 4 is 2, because 2 times 2 is 4. And the square root of 9 is 3. We can say plus or minus out in front of both of these, plus minus. But the bottom line is 2 times 3 we get 6 still, plus or minus 6. So a unique property of radicals, and this is what we refer to as the product property, says this, just like we had mentioned just now, but it says if you take the square root of the product of 2 numbers, we say a and b here, that is the same thing as the square root of a times the square root of b, and this is a very useful property. Now likewise we could discuss maybe a quotient. Okay, so maybe as far as a quotient goes, we could go with one, we know some square roots here, but we say what if we took the square root of a quotient of 4 over 9? And the square root of 4 ninths, we say, what could I take times itself to get 4 ninths? Well, I could take 2/3 times 2/3. Okay, and we could check this. You know, you take 2/3 times 2/3, you just multiply it straight across, you get 4 ninths. 2/3 times 2/3. But the bottom line is this. We say, well, we could also say the square root of a quotient is a quotient of the roots. And so we say square root of 4, well, that's plus or minus 2. And the square root of 9, that's plus or minus 3. 3 times 3 is 9. So what we're trying to illustrate here is this, what we call the quotient property of radicals, quotient property. And as we've just, you know, previously mentioned, the quotient property states that if you take the square root of a fraction, really, you know, you want to call it a quotient or a fraction, that doesn't matter to me, we say it's the same thing as square root of a is square root of b. Basically, the square root of a quotient is the quotient of the square roots. So these two properties, we're going to pick on them quite often, and they're very useful. You might say, well, what? You know, when are they useful? If you've taken a geometry class before, you probably had to do a lot of simplifying of radicals. But we say, what if we had something like this? radical 72. And I want to simplify this. So this is not in simplified form. And the reason why is because there is a perfect square that proceeds into 72 evenly. That is, you might say, well, you know, it's a multiple of 4, and it is a multiple of 4. But even better, we could say, excuse me, is it a multiple of 4? 2, yeah. Yeah, anyway, we could say this is the same thing as 36 times 2. 36 times 2. And I say 36 times 2 because we know the square root of 36. The square root of 36 is, well, 6 times 6 is 36. So we could rewrite this as the square root of 36 times the square root of 2. And the square root of 36 is plus or minus 6. And then we would just leave the radical 2 because there are no perfect squares that proceed evenly into radical 2. So this would be referred to as the simplest form of the radical 72 that we had started with. Okay. So that's kind of a long way of writing that out. This is like example A here. Let's do another example. What if we were to consider maybe radical 18? Now, this is a little bit more common, maybe example, but we want to say, well, are there any perfect squares that go into 18? Those are things like 4, 9, 16, 25, you know, 36, you know, name it, 49, whichever one you can think of. But we say this is the same thing as radical 9 times 2. And we say 9 times 2 because 9 is a perfect square. We know the square root of 9. So instead of actually splitting this up this time, what we'll do is we'll just say, well, you know, square root of 9, we'll cross that off, and we'll put plus or minus 3 out front. And so the simplified form of this radical is radical, you know, plus or minus 3 radical 2. And those are our two roots. Okay. Likewise, we can do the same thing with, say, a radical of a quotient. Now, what if we had like radical 7/16? We do actually want to split this one up. We can say the same thing as radical 7 over radical 16. And we know radical 16. Radical 16 is the same thing as radical 4 squared, or the square root of 16 is 4 because 4 times 4 is 16. But we say this is a radical 7 on top, and then we say plus or minus 4 on bottom. And that would just be our simplified form right there. Now, it's a little bit different when we deal with something like, say, radical 2 over radical 7. Now we're dealing with something where when we split this up, we get radical 2 on top, and we get radical 7 on bottom. And quite technically, these are both plus or minus, you know. So we have two roots for each. But the bottom line is this: we don't like to have radicals in the basement. So what we're going to do is a method that we call rationalization. We're going to rationalize our denominator. Okay, this isn't the same thing you do when, like, you had to buy a red pair of shoes because you didn't have a pair of red shoes, and you rationalize it to yourself. This is rationalization with respect to the denominator here. So the method is this: whatever radical you're stuck with in the basement, you know, we don't know the square of 7. There are no perfect squares that go into it. What we're going to do is we're going to square the bottom. Now, the thing is this: you can't just take a fraction like, say, 2/3 and square the top and square the bottom and end up with something that's equivalent to what you started with, because let's see, you know, 2/3 squared is 4/9, and 4/9 is not the same thing as the 2/3 we started with. However, what we could do is we could take, for example, 2/3 times 1, and it would stay the same, except for, you know, what if I took it times 2 over 2? This is just an example. I mean, I'm just making this up here. But I do know this: 2 over 2 is the same thing as 1, and anything times 1 is itself. So in this instance, we'd get 4 over 6, which is the exact same value as what we started with. So if we know this, we have a radical in the basement, and that's entirely undesirable. You don't want radicals in the basement. Then what we'll do is we'll square it. But you know what? Square means takes it times itself. Take it times itself. So we'll take the bottom times radical 7. But we also need to take the top times radical 7. Okay, so what we get here is this: radical 2 times radical 7. Recall that you multiply two radicals together. That's the square root of just the product of those two things. So now on top we get radical 14, because that's radical 2 times 7. And on bottom we get radical 7 times radical 7. Now that is the same thing as radical 7 squared. And you know, when you square a square root, those things, they cancel each other out, and you're left with just 7. So now we have plus or minus radical 14 over 7. And I think it'd be good to go through like maybe one more example of rationalizing a denominator here. So maybe like a simpler example, we say like radical 3 over 5. So again, we would split this up into the quotient of the radicals instead of a radical of a quotient. So we get radical, this is all plus or minus, radical 3 over radical 5. And because we need to rationalize the denominator here, this is our method here, we're going to rationalize this by taking it times radical 5 on bottom, but also times radical 5 on top. Recall, you know, what you do to the bottom of a fraction, you need to do to the top. Let's do the bottom first this time. In this instance, we end up with radical 5 times radical 5, and this just ends up simply being 5. And on top, we get radical 3 times 5 using our product property. That's radical 15. And since this has 2 roots, we'll say it's plus or minus radical 15 fifths. So these are some basic properties of radicals and just basically how they operate. And this will be good leading into the next video when we are solving quadratic equations using square roots.